Cool. I think we're ready to go, Philippe.
Yeah, let's go.
That's you then, Philippe, or?
What?
That's you then, right? to introduce Xiaoping.
Up to you.
Yeah.
Oh, but so everybody is already in?
Yes,
I
think
can't
so.
see the names. Oh, okay. Sorry. Yeah. This is okay. Welcome everyone. It's I was a bit destabilized by the fact that in this uh, in this Zoom setting we don't see all the participants. But so yes, welcome everyone. So for this new webinar, eyes of for ICAR. So the last time we had Nick Webb speaking about interaction between vegetation and Aeolian processes, and this time we have the pleasure to have Xiaoping Yang, who is going to present some work on paleoclimates. And so it's a great pleasure to introduce you. So just a few words about you, Xiaoping. So to tell the audience. So you did your PhD in Germany. So yeah, apparently you speak very good German. Hopefully you speak also very good French. We'll see. So yeah. Now you are a professor at the School of Earth Science in Zhejiang University in Hangzhou, and before that you were in Beijing at the Institute of Geology and Geophysics. And so your main interest is about geomorphology in general and quaternary environment changes. And so we are very happy to have you here for this seminar. At the end of your talk, there will be a possibility to have questions and answers. So for this, you should use the Q&A button at the bottom of the window. And that's about all what I wanted to say. Maybe my co pilot on this on this plane, Andrew and Jan Beren may add a few more things, but otherwise I think we are ready to go for Xiaoping's talk.
Yeah, maybe
Yes.
some words. We start these virtual Aeolian sessions as a means to keep meeting even during the pandemic times. And initially, this was we started these seminars with really seeing each other or meeting each other by all switching on our cameras. But we're struggling a bit with the Zoom functionality here. So maybe this is not possible at the moment. Maybe for next time we can set this up again. But other than that, nice to meet you. I hope you can see Xiaoping is the main star today. So I think, yeah, Andrew, maybe you have some. We can start maybe sharing and Xiaoping screen or.
Yeah, maybe Xiaoping can try and share his PowerPoint. We can get it up. Yeah, just before we fully start, I just want to say that yeah, here we go. This is actually perfect. This first slide that Xiaoping's kindly embedded in his presentation. It shows he's the second of three seminars, which are sort of a trio creating a small mini series, I guess, which are based on three topics that we thought were pretty well represented, ideas that were or areas that were talked a lot about at ICAR, which was the ICAR conference last year in Las Cruces, New Mexico, in the US. And yeah, we already had Nick's talk, and we're hopefully soon going to have that available online for people to watch. And the third talk is by Cheryl McKenna Newman and Joe Neild, and their talk is going to actually be in June, but the date is yet to be completely confirmed. But they're finally going to talk about measurements in Aeolian research in the field and in experiments. And Nick talked about vegetation and I would say, yeah, vegetation and applied geomorphology in that respect. But anyway, that's all I want to say. And I think we're ready. Thank you very much for presenting, Xiaoping, and you can take it from here.
Thank you, Philip, for your very kind introduction. Thank you, Yang and Andre, for your encouragement. It's indeed a great pleasure for me to talk to you today. On the title, Paleoclimates Studied by Aeolian Deposits, I have a lot of ideas, and I think you do too. So first of all, I would like to say good morning to those who just get up, and good afternoon to those who have lunch, and good night to those who are going to go to bed. Hi, everyone. Today, I would like to share first my experience from last ICAR, in particular from the session Palaeoenvironments. Then I would like to share with you my understanding in inferring true accumulation rates from dated Aeolian deposits, reconstructing wind paleoclimate using present-day dune patterns, decowoven changes in aridity and wind stress in Aeolian deposits with a special reference to Chinese deserts. And then I would like to explore with you the potential new proxies for studying Aeolian deposits, our experience and success in incorporating paleoclimate simulation with large spatial and temporary grading into Aeolian studies, and our understanding of paleoclimatology through studies of modern active Aeolian systems. I'll try to shift the next slide. What works? Thank you. It's a great honor for me to be one of the co-conveners for the Palaeoenvironment session at the last ICAR. Fortunately, all the information, in particular the oral presentations, are still available from the conference website. We had luckily 4 or 6 oral presentations and 4 or more posters in that session. The first presentation was given by scientists from Australia. They studied, I hope you could see the title of this presentation, or should I close somewhere?
No, it's okay. No.
Is that okay? Good. The first was about a core from Mercure, Iceland, located very close to Antarctica. The scientists dated the core 3 meters in thickness with lead 210 and radiocarbon. What impressed me most was the final results from that study. They found that mineral input from a distant source increased between 4.6 to 3 Ka, and also 3 times during the last 800 years. This is a peak for mineral input, that means related to dust emission. As the conference took place in the USA, we had 3 presentations about study sites located in the USA. One was talking about Sonora Desert, Arizona. It's a joint work between Israeli and American scientists. They found that during the mid-Holocene drought, dust flux were minimal and dominated by summer sources until dust input ceased, as drought conditions did not produce enough floods to refill sources with sediments. Usually, I thought that dust is related to aridity, but in this presentation, I learned that the availability of sediments is even more important. In this case, the availability of sediment decides the dust flux. That means more dust during wet seasons. Another study is about Central Great Plain, USA. The scientists under the leadership of Professor Mansell and others found out that late Holocene Aeolian activity associated with more frequent multi-year severe drought, but enough intervening wet years to sustain vegetation on loess tablelands. In contrast, pure and route explored by sand transport and other sources of hysteresis in dune activation and stabilization sustained dune activity for decades to centuries over large areas. In brief, during late Holocene, vegetation sustained on loess tablelands, but dune activity was severe and even long over large areas in part of the USA, in particular in Central Great Plains. My co-convener, Steve Wolf, studied dunes in East USA. He found out that dune field activity is recorded between the last glacial maximum, in particular between 23 to 17.5 Ka. South-border dunes appear to have remained active in this part of the world as late as 13 Ka. They found out that dune stabilization coincident with northward retreat of Laurentides ice sheet, the well-preserved dune morphology and narrowly constrained edges within dune fields suggest rapid dune stabilization in East United States. This is a very interesting talk, and I'm happy to know that our co-convener is among the audience. The title of the presentation is Climate Memory in Giant Dunes. From study of Andrew's work and his collaborators found that a diversity of cases for Earth's modern giant dunes. Some where climate has been remarkably consistent through the glacial cycles, very surprising. Some where climate has changed, but dune morphology has equilibrated to modern climate, like the case in Egypt. And some where the dune morphology represents an old climate and not the modern climate, like the case in the Saudi Arabia. As it was an international session, we have also sessions or the talks about European sandbed. As we know, there are not much active dunes in the European continent right now. But from studies of Polish scientists, we know that dune fields developed in a single phase. Probably these dunes were not stabilized even during warm periods and were formed continuously over a period of several hundreds to even several thousand years. It is likely that the entire late glacier was favorable to intense Aeolian process in Poland and beyond. The last presentation in that session was given by me and my co-authors. We talk about the Taklamakan. I'm very grateful to National Natural Science Foundation of China for granting me a new project that enabled me and my team to continue to work actively in this amazing desert. I should tell you that there were several great posters in this presentation, as I said, at least 4, but I cannot read those abstracts on the website anymore. Otherwise, I'd be happy to share with you with my experience. And they're great posters indeed. Now, I would like to move your attention about inferring true accumulation rates from dated Aeolian deposits. Whether we could find true accumulation rates, I think it's a site-based issue. From sand sheets like the sandy land located in the east part of desert belt in North China, that's okay. We were fortunate to be able to find out sedimentation rate, that is accumulation rate. In other words, in such a sequence, we can say that from early Holocene, the accumulation rate was higher, decreased during the mid-Holocene as paleosols developed, and increased again when Aeolian activity became dominant. It's not a simple issue. Sometimes it's quite difficult indeed. Like the case in the same study area, we dated the Aeolian sediments, in particular in the case with dune sediments. For example, this over-meter Aeolian sand were deposited in less than 200 years. But this half-meter Aeolian sand or dune deposits were formed in the last 2,000 years. So I found it's very difficult to have accurate or acceptable or reasonable deposition rate from dune sediments. The same happens even with lacustrine sediments in this environment. We can see from ages. Some of the lacustrine sediments were formed quite rapidly. This over 1 meter formed just in several hundred years. Others may be formed much longer, even roughly 5,000 years. So I think this is a site-based issue. We do not have general opinion, but we could be able to find it by careful study of the study site. This is even more difficult when whole time scale is considered. Here is a base age of dunes from different deserts: South Kalahari in South Africa, Terraria Desert in Australia, Straggles Desert in Australia, Negev Desert in Israel. We can see that the base ages of dunes in Kalahari changes a lot from several thousand years to around 200,000 years. By the way, the arrow indicates minimal ages. So the some of the base is even older than 200,000 years. Some from the same dune field are only a few thousand years. Similar happens with Australian deserts too. By the way, the defect density refers to the terminations and junctions counted within a radius of 5 kilometers. This is very impressive work published in Geology. I hope you could see the author's name too. He's in the audience. I think this is mainly based on physical calculation and mathematical calculation. It's about Rupkali Desert. A is a distribution and map of deposition rate. We can see that in places that have high deposition rate, in other places have much lower deposition rate. With minus, I understand that it refers to places where erosion takes place. Here's the migration speed. Again, in the same dune field, some places have quite fast migration and others with much slower. Here's the formation time, log. FDP refers to probability density function, and with unit millions of years, some have much less than a million years. Others, dunes may be as long as 10 million years old. Here is a reorganization time. Again, some dunes reorganize very fast and some very slow. I had a little bit difficult with change of slides. I'm sorry. I hope that will not disturb you. It works. This is a collaborative work under the leadership of Nick Lancaster that shows histogram of all luminance ages archived in the ICAR Dune Atlas chronological database. You can see that younger than 50 Ka in the database are dominant, and in particular, strong influence of taphonomic decay on the distribution. A lot of ages are younger, the older ages are much fewer. So here we call it with an exponential decay of ages with time. So many of the ages are young, so that is again challenge to calculate precisely the accumulation rate. Now I would like to talk with you about reconstructing paleoclimate using present-day dune patterns. Present-day dune patterns tell us a lot, as I mentioned earlier today, by a presentation given by Andre, talking about memory of giant dunes. From this slide, we can see that there are different spatial scales and time scales in reality. Reapers may be formed in a shortest period of time, days. Dunes formed normally several years. Mega dunes, dune fields, sand seas requires 1,000 to 100,000 years or even longer. The spatial scale increases with the temporary scale, so that helps us to understand dune patterns to a certain degree. I tried. Good. This is collaboration work between scientists in Aachen, Germany, and my group in Hangzhou. And the work was mainly done by Lucas. He was successful in mapping the dune migration in the Gonghe Basin of Tibetan Plateau. The map, this is also in collaboration with British scientists. I should mention that too. The map dunes in the Gonghe Basin are experiencing an overall decrease in migration rates by 1.8 meters a year with a study period of past 52 years, as we used the coronal satellite image that was the oldest image we could obtain for this study. This is in accordance with the decreasing RDP values calculated from ERA 5 climate models. So ERA climate models indicate decrease in wind speed, and Lucas was able to find out that the migration speed of dunes decreased too at the same period. However, the map dune migration direction is in good agreement with the wind direction. It's a very useful work to my understanding. In the Aeolian landscape, we couldn't find a lot of memories, in particular past environment changes. These dunes are stabilized by vegetation at the present time. In this dune field, if we look closer, we could find laminations like this, and we can find also aquatic biotopes like diatoms in these sediments. Although they look like Aeolian sand, they were initially formed in lakes. We call them as lacustrine sediments. From the digital surface model, we could understand that there were paleo lakes in this dune field, and there were channels connecting these lakes. The channels we investigate in the field look like this, totally consistent with the digital surface elevation model. We found that the headwater erosion or groundwater sampling probably made aridification of this landscape. The old channels we found in the field can be reconstructed from this surface model you can see the changes of valleys is consistent with classic geomorphological knowledge. So in this sense, not just Aeolian, but also fluvial process shaping the Aeolian landscape. So we can learn a lot from Aeolian landscape. More reliable, of course, are site-based scale. For example, Navajo sandstone in Utah is a work published in sedimentary geology. You can see the striking of the dune slopes and the direction, and is totally consistent with this figure. The common changes in aridity and wind strength in Aeolian deposits is not an easy work from my experience. You might know that Banda-Yaran Desert probably holds the highest dunes on our planet. The work done by Professor Deng and his collaborators defines that there are different orders of the Aeolian landscape, order 1, order 2, order 3, and this might reflect changes in wind. I, however, believe that the changes in aridity also played a large role in shaping the landscape. This is a collaboration between Professor Martin Williams and me, and we were able to reconstruct Holocene high lake levels in this dune field. For example, there used to be a huge lake in this interdune area. Now just smaller remains here. So again, I found it's difficult to make difference between aridity and wind strength in the desert environment. It will become easier if we see a clear sedimentary changes, like the case in Kumataga Desert. We were able to find a section located somewhere here, and we see clearly fluvial sediments interbedded in the Aeolian sequence. For me and for my collaborators, we believe that the fluvial sediments were caused by rivers, as these rivers indicate the increase in moisture. So again, if the sedimentary facies changes, I would prefer to interpret the changes in effective moisture instead of wind power. Professor Jürgen Höfermann was one of pioneers who were able to study the global scale patterns. Aridity and wind strength often interact. From his work, published already 40 years ago, roughly, he found that in north part of Africa, the arid landscape was larger not only horizontally, but also vertically. In south part of Africa, the aridity is much smaller, both vertically and horizontally. So that is due to the effective moisture changes. I'll go to next slide. This is one of the amazing deserts where I like work very much. The extensive Aeolian landscape in this desert, and you can see that there are also ancient towns like 1, 2, 3, 4, 5, all refer to ancient civilization places, quite advanced already 2,000 years ago. And the yellow square indicate places where we have worked intensively. Usually, we try to understand Aeolian geomorphology with first mapping the wind power changes. The wind power changes can be best explained, to my knowledge, with Freiberg equation. We use resultant drift potential, and those with the strength of wind power. You can see clear the changes of wind power within the Taklamakan Desert. This is the Aeolian landforms map published by Professor Jujenda good 40 years ago. Is still valid to a large extent. He was able to find giant dunes in this part of Taklamakan, this part of Taklamakan. Note that the previous slide shows strong wind here, but not in these places. So not only wind, but other factors may have an impact on the Aeolian landforms. Taklamakan is very fortunate in many aspects. In particular, it's a desert with many inflow rivers. One of the rivers is named as Nia, with headwaters in the South Mountains, and it's roughly 200 kilometers long. It reflects a very complex hydrological system, which I would like to share with you. From satellite image, one would imagine extensive dunes in this vast area. But if we go into the desert, it's not difficult to find sections like this, lacustrine sediments underlying dune signs. We were very fortunate to be able to dig several profiles in this desert, like A, B, C, D, etc. I would like to explain a little bit about the case of the figures. The yellow indicate Aeolian sand, and this color is the fluvial deposits. This is slackwater deposits. This is lacustrine. In this desert, we were able to find many profiles with lacustrine, fluvial, and slackwater deposits. We were able to date them with optically stimulated luminescence. This area again is interesting from large scale. Earlier, Professor Hefferman was able to identify the former extent of glacial fluvial fans in the farmland areas of the Kunlun Mountains. He defined the oldest glacial fans and the youngest glacial fans and the middle-aged. So of course, this needs absolute chronological dating. I hope that could be dated in the years to come. What we found in the dune profiles, as I showed you in previous slides, we could map all the green bars. The green bars with fluvial sediments or lacustrine sediments marks most periods to my understanding. And we try to explain why this happened in such kind of cyclicity. Here we use temperature anomalies in comparison to that of the last Ka, reconstructed using delta D in the ice core of the Antarctica. Here is our new calculation with 5 Ka year time window. The orange color shows distinct warming, and the blue color shows distinct cooling. We were able to find that the wet periods are often coincident with global warming periods. Here's the enlargement of the Holocene period. The ancient civilizations or the towns I showed you earlier in the slide was all identified roughly in the period where climate was wetter than at present. Talking about potential new proxies, all of us trying to find new proxies for our research work. Usually for Aeolian community, everyone uses grain size. Grain shape parameters could be useful, but was not widely used earlier because of difficulty in measurement. The definition of sphericity, symmetry, aspect ratio, and convexity are defined by these authors. We are able to precisely calculate these parameters now using a new machine by capturing the images of millions of grains using high frame rate camera and image analysis techniques. try to get next slide. That's not good. Thank you. Peng Liang and I did a joint work in the eastern part of desert belt in China. If you look at the grain size parameters, different facies are mixed in this figure. But if we consider the shape parameter aspect ratio, is slightly clear Aeolian sand in the upper part, but we use both shape parameters, spherosphere and azimuthry. The Aeolian sand are located here, and other sediments can be found here. So to my understanding, wind blow sand is more spheric than the river sand in the mountains. This obvious difference can be used to clarify the traveling history of grains. This could be a potential new proxy for us to understanding sedimentary facies, in particular in Aeolian studies. Another parameter I would like to suggest is not new, but may be new for Aeolian community. Trace elements, for example. Trace elements can be very useful for identifying sources of sediments. To my experiments, these two smaller catchments, Tyler River and Korea River, are very close. If we compare the trace elements in coarse sand, they are different. That's probably due to different catchment. But if you compare the fine grain size sediments, both are quite similar. This tells me that the wind played a large role. As I previously showed, the wind from north may mix the sediments. So the trace elements can be a potential indicator for us to precisely identify sources of sediments. In that context, the changes of wind direction. Referring to paleoclimate simulation, we know that all simulations are with large spatial and temporal grading, and our Aeolian studies are very often site-based. How could we make use of them? I would like to share you some of my experience and some work done. Just a very brief, the abbreviations. CMIP refers to Carped Model Intercomparison Project. PMIP refers to the Paleoclimate Modeling Intercomparison Project. There are many models in the world. We try to find the models that best fit our research purpose. In this case, we found that this model, for example, can be used for our study, and this model, and sometimes use average values of these two models. How could we make use of this? For example, several of us read the literature very carefully, found that during the last interglacial, that means 1027 Ka, these areas were quite wet. Not only in western part of Alashan Plateau, but also in the valley of the lakes in the Republic of Mongolia. So we try to use model to understand why. This is a modeling from average value of two models. The model indicates that this is a study error, as I showed you previously. At the time of the last interglacial, the moisture from Indian monsoon and East Asian monsoon were able to reach this area. So the modeling helps us to feel confident that the evidence we found in the desert indicates something indeed. We know that there are clear variations from place to places. We use dual mobility index to understand the Aeolian morphology, compare pre-industry control with mid-Holocene. We found that there's a clear shrinkage of dune activity. Here indicate 4 levels of activity. The white line indicates the pre-industry situation. All this can be found the difference. in the most parts of China, in North China, the dune mobility index decreased during mid-Holocene. Only in the western part, some places like the western Taklamakan, there was an increase. In the eastern Gobi Desert, the evidence of large shorelines and lakes, we were able to date them with various methods and found two particular wet periods. One is a marine isotope stage 5, another was mid-Holocene. We tried to reconstruct the variation of precipitation, and we used the lake evaporation 900, 1,000, 1,100. By the way, this is the current average on mean precipitation in this area. From our simulation, we could find that during high lake level, the precipitation was much higher, 2 to 3 times more than at present time. Why we use the evaporation value like this or like this, not much higher? That is because we are aware that in literature, people describe evaporation in deserts about 3,000 or sometimes around 2,000. And sometimes one make difference between land surface and lake surface. We use the classical model, modified Penman equation. It's widely accepted in hydrology. All of these parameters can be calculated separately. EL means evaporation from lakes. We were able to collect data from weather stations about radiation, temperature, air pressure, vapor pressure, wind velocity, sunshine duration. And we know that in the deserts there is no weather station. Using reanalysis method, we were able to calculate the weather data for our target area here. From our work, we come to the conclusion that the mean annual evaporation from lake is not that high, just around 1,000 millimeter. From land surface, we believe it's around 100 millimeter. That's why I insist that we use 1,000 roughly as evaporation for our simulation earlier. I'm aware that this kind of estimates are associated with errors. As Alexander Humboldt said earlier, an approximately correct answer is always preferred to an exactly wrong answer. And I feel that we try to get an approximate correct answer to the reality. Understanding Aeolian paleoclimatology was studies of modern active Aeolian systems. This is a very nice work to my understanding. The fact that the interaction index is a function of space, therefore a function of time. Wind regime and sediment supply are the primary boundary conditions determine the density of interactions. And also in this paper, I found that the sediment supply can be affected by many factors. To my understanding, effective moisture is one of the key factors deciding sediment supply. So we have a chance to understand paleoclimatology from modern active Aeolian systems, indeed. For our field research, now our society comes to an era of big data. Big data is very useful, in particular in the time with artificial intelligence. But I would just remind you that even in big data, there are some mistakes occasionally. Like early season dust storm hits Beijing was published at the day of the dust emission. The satellite image indicates that dust was from Taklamakan. Our detailed fieldwork and analysis denied this kind of conclusion. And in the big data era, I think we still need to do detailed fieldwork. Like the work, this one, you can see bedrock in the dune field only if you look very carefully. I was very pleased to read this book, 9-Word Sahara Science Adventure of a Geomorphologist at Large, written by Martin Williams. I think study the science is exciting. And experience the field is also exciting. I think for the field research, we need a combination of big data and the traditional scientific methods. Both are important. One could not replace another, to my feeling. To conclude, I'd like to share with you that Palaeoenvironment session at last ICAR was very helpful, insightful, and valuable, although I was not able to reflect all aspects at that session today. It's not straightforward to obtain true accumulation rates from Aeolian sequence from my experience, but I think with a careful assessment, it's likely to obtain knowledge closer to the truth, however. We all get a little bit more about the truth through our detailed study. Compared to wind stress, effective moisture might be sourced from other regions, like the case in the Taklamakan, seem to be more decisive in shaping the environment in Chinese deserts, maybe in other deserts too in the world. Referring to new proxies, I believe ground shape parameters and sediment province could be considered as potential new proxies for studying Aeolian deposits, particularly with respect to changes in winds. A correct understanding of the basic hydrological process, like I showed, the evaporation rate from lakes, is essential for interpreting paleoclimates from Aeolian landscapes. Paleoclimatic simulation can be helpful for understanding mechanisms of climate change in Aeolian systems and could helpful to find knowledge gaps for field research. May I thank you all for your attention. Thank you.
Thank you very much, Xiaoping, for this very nice presentation. So now we open the questions and answers session. So once again, if you have questions, you can type them in the Q&A section of the Zoom, and but you will not be able to speak, but only to write them in this window, and then we can gather them or ask them on your behalf.
That's right. Yeah.
Meanwhile, we may start with our questions, maybe, waiting for the question from all other attendees. And Jan Berend has a question.
Yes, thank you very much, Xiaoping, for a really extensive overview. Well done. I have a couple of questions actually, and I'm using the privilege of being in the panel to be the first. You've been around since 1992, right? Since you defended your thesis in Germany, so that's 30 years. That's almost a time series by itself. So that's impressive. And I was wondering if you have seen any developments over those 30 years in the methods and in the you mentioned proxies and new proxies, but maybe you didn't really touch on dating, and I know you worked on that. Have you seen any improvements in those dating methods maybe and provenance also? Could you comment on that?
Yeah. Thank you, Yang. Thank you very much for kind words. Indeed, the dating has revolutionized in the past 30 years. As I was a PhD student, I used to steal radiocarbon try to date Aeolian sequence. At that time, TL was widely used. But I think in particular, since 2003, the SAR method was widely accepted by OSL community. And I'm pleased to tell you that we even have an OSL lab in our campus right now. It's in function since last October. There's a huge advancement in chronology nowadays. First, actually, it's for a new talk. My colleague Peng Liang, who studied OSL with Stephen Foreman in Baylor, he was able to date quite young sediments, even the sediments deposited in the last 50 years, and compared with satellite image that was quite accurate. And we were able now to extend the chronology to 500,000 years, to my knowledge, for some Aeolian deposits, and more precisely for Holocene period, I would say. So there's a huge advancement in chronology, not only OSL, but also we try to use other methods. There's actually a huge change as Nick Lancaster launched the effort to set up Dune Atlas chronology database. At that time, the number of OS ages were limited. There's a rapid increase in recent years. I think the significance of Aeolian deposits for paleoclimate is underestimated earlier, but now become more attention. By the way, I may share you some personal experience. I was very fortunate to study with Professor Jürgen Höfermann. He had a long research life. He lived until 102 and did research for a long time. He was one of the early initiators for German paleoclimate research. He was in close collaboration with Klaus Haselmann, who received Nobel Prize for Physics for paleoclimate research, I think 2 years ago. Actually, there's a teamwork to my knowledge. As our student, Höfermann went often to the paleoclimate workshop and chatted with Klaus Haselmann about models. Thank you.
Thank you very much.
Oh, okay. Please do type your questions in the Q&A window. Oh, there is one.
Should I read it, Philippe?
Yes, please. You have a better accent.
So Xiaoping, maybe you can see this, but Sui Hua Che, I think that's how you say that. I'm sorry if I pronounced it wrong. Asked a question. Hi, Professor. I wonder if we can infer a threshold of mobile and dormant dunes from the Aeolian deposits record, and if this threshold can be seen now from the geomorphology. I think they
thank you.
Potentially mean the threshold wind speed.
I think threshold mobile and dormant dunes. Threshold, to my knowledge, I think it refers to the mobile dunes. It's with dormant, it does not have issue with the threshold. I think that is related to our previous talk, vegetation. The dormant dunes is dormant partly due to stabilization by vegetation, or to a large degree by vegetation. So wind actually occurs in every places in the world. Also in Hangzhou, where I'm based now, there's no dunes in Hangzhou, not because the lack of wind, but because lack of bare surface. So luckily, I think threshold refers only to the active dunes. To the dormant dunes, activation is probably not by wind, but by overgrazing, for example, or by cultivation to a larger extent. I hope I answered this question. Thank you.
Okay. You continue reading, Andrew? Oh yeah.
Sure.
Two more questions.
Yeah, there are two more. So Patrick Hesp asked a question. Is there a relationship between the presence of Nebka and rainfall or climate? So Nebka is the sand deposit behind vegetation, if anyone in the crowd isn't familiar. Yeah.
Thank you. I think that's a very important aspect to see Nebka or dunes, smaller dunes stabilized by vegetation. But to my knowledge, NEPCA could occur in many different climate zones. In places where rainfall is high, and in places where rainfall is very limited. I know, for example, NEPCA stabilized by Nitria, a kind of shrubs in the Alashan Plateau. That is more due to groundwater. The shallow groundwater is able to sustain shrubs that could help to maintain NEPCA. I saw also NEPCA in much wet environment, semi-arid areas like in the east part of Inner Mongolia, where rainfall is around 400 millimeters per year, but there are still NEPCA. So I think as NEPCA, to my knowledge, is not a typical landscape, but is very often a single or group of smaller stabilized dunes. So there's no sharp boundary in terms of current rainfall. Thank you. I hope I have answered that question.
Thank you.
Thanks.
Third question. Yeah.
Yeah. Ashok Kumar Singhvi asked a question. They said, nice talk, compliments. What exactly do we learn from accumulation rates, given that they are based only on the preserved records? Provoking question.
Thank you, Ashok. I'm very excited to know that you are among the audience. Ashok, as I think many people know, is the first person who have used TL dating dune science. His cutting-edge research has encouraged many young people, including me, to do the work. Now, the question is again a very insightful question. As just preserved records. So what could we exactly learn from accumulation rates? I think from my experience, we learned something about local-sized climate changes. But for me, it's always challenging to disregard erosion in the accumulation rates. I think that's a very difficult aspect, and people do this kind of work, so do I, and I hope that in the years to come, we could have more deeper insight in this regard. Thank you, Ashok, for your coming. It's very encouraging. I appreciate your question and your presence. Thank you. It's a pity that I can't see you, but I say hi.
Okay.
We have all the questions.
I have myself a question, if there is still time. I think
so.
We can, yeah. So my question is, well, first of all, thank you for this talk. I said this already. My question is the following. So I understand that it may be difficult to interpret the observations if you're not sure about the processes, whether the wind is stronger or humidity is larger. So if you want to go beyond the observations and the difficulty to interpret them, is there a way to do experiments with not with a true system, obviously, because it's over a long time scales, large length scale, but on something that would be an analogous system where things go faster, quicker, or at a smaller scale, in which you could test, similar measurements? Is there a way to do a kind of downscale system on which you could work to improve what you are doing?
Thank you, Philip, for your very hard question. Actually, I would say that you know the answer as a physicist and modeler. I think I agree with you and others who use physical modeling and numeric modeling to make the experiment shorter and more effective. I think that helps us. On our campus, with our university, Zhejiang University, is setting up experiment system we call the ultra gravity experiment. So with a huge gravity, many times larger than the reality, we want to speed up the geophysical process on the Earth's surface. That is still in test period. For example, I think with a small scale, with a similar physical association, we could test the changes of Aeolian landscape in a predictable time framework. Like I introduced the work published by Andre, shows the accumulation rates, reorganization time. I don't think we could really observe this reorganization time, but with a physical background, I trust that that's a useful approach. Thank you.
Okay, thank you. Any other questions from the audience or from the panel? Oh, we are done, right? Yeah.
I could probably ask questions for another half an hour, but I think that we are past 6 o'clock, so we should probably finish.
Yes. Okay.
Yes.
Okay. So thank you very much, everyone, for attending this webinar. Please note the next one. The next one will be in June, not in May. In June, next June, by Cheryl McKenna-Neumann and Joe Niels on the measurement techniques, comparing experiments and field techniques. So that will be very interesting as well. That's about what I can say, right?
Yeah.
And so bye-bye, everyone, and thank you again for attending.
Thank you all. Thank you. Bye-bye.
Thank you very much. Bye-bye.
See you someday. Thank you.